A star exists so monstrously vast that placing it where our sun sits would swallow Mercury, Venus, Earth, Mars, Jupiter, and Saturn whole. Yet the average cubic meter inside this object contains less matter than the best vacuum any laboratory on Earth has ever produced. Today, we journey inside Stephenson 218, the largest star ever confirmed, to discover how nature builds a monster that defies everything we thought we understood about size and the limits of physics. Let's begin. In 1609, a mathematics professor in Padua pointed a crude tube fitted with glass lenses toward the night sky and shattered a boundary that had constrained human knowledge since the beginning of civilization. Galileo Galilei saw mountains on the moon, phases of Venus, and 4 bright points circling Jupiter that no human eye had ever detected. His telescope magnified objects roughly 20 times. The entire instrument weighed less than a pair of modern binoculars. Yet that modest arrangement of glass proved something that would echo through every generation of astronomers to follow. The universe contained more than naked eyes could perceive, and the right tool could drag the invisible into view. 3 centuries later, Edwin Hubble sat at the eyepiece of the 100-inch Hooker telescope on Mount Wilson, high above the lights of Los Angeles. The year was 1924. Hubble identified individual Cepheid variable stars within what astronomers then called the Andromeda Nebula and calculated their distances. The numbers placed Andromeda far beyond the boundaries of our Milky Way. In a single measurement, the known universe expanded from one galaxy to an uncountable multitude. A larger telescope had once again revealed what smaller instruments could not reach. The pattern repeated across the 20th century with a regularity that felt almost like a law of nature. The 200-inch Hale telescope at Palomar Mountain pushed the visible frontier deeper into cosmic history. The Hubble Space Telescope, launched aboard the Space Shuttle Discovery in 1990, delivered images of galaxies more than 12 billion light-years away. Each generation of instruments extended human sight further across space and deeper backward through time. The lesson seemed clear and absolute. Build a more powerful telescope, and nothing in the cosmos can remain hidden. That lesson is wrong. There exists a star in our galaxy so luminous that it outshines 440,000 suns combined. Its total energy output ranks among the highest of any stellar object in the entire Milky Way. If you gathered every photon this star emits and measured the sum, you would find a radiance staggering enough to dominate the infrared sky across thousands of light years. And yet no optical telescope ever constructed, not the Hale, not the Hubble, not the most advanced ground-based observatory operating today, has ever detected this star. Not once. Not a single photon of visible light from this object has ever registered on any instrument designed to capture the wavelengths human eyes perceive. The star is Stephenson 218. It burns roughly 20,000 light-years from Earth, buried behind curtains of interstellar dust so thick that they swallow 99.999999% of its visible light before that light can reach us. Astronomers quantify this obscuration using a measurement called visual extinction. For Stephenson 218, the extinction reaches 20 magnitudes. That technical figure translates into something easier to state, but harder to accept. The intervening dust dims this star by a factor of 100 million in visible wavelengths. Imagine trying to see a candle through a wall of fog 100 million times thicker than any fog that has ever formed on the surface of Earth. The candle burns, the light exists, but the fog devours everything. How then do we know this star exists at all? The answer requires a different kind of light, one that human eyes cannot detect, but that passes through cosmic dust the way sunlight passes through window glass. Dust grains drifting through interstellar space measure roughly 1 micrometer across, comparable in size to the wavelength of visible light. When electromagnetic radiation encounters particles of similar dimensions, A physical process called scattering occurs with punishing efficiency. Shorter wavelengths scatter more aggressively than longer ones. This same principle paints Earth's sky blue during the day. Blue light from the sun bounces off atmospheric molecules far more readily than red light, flooding the overhead sky with shorter wavelengths. It also explains why sunsets burn red and orange when sunlight travels a longer path through the atmosphere near the horizon. The blue wavelengths scatter away, and the longer red wavelengths survive to reach your eyes. Interstellar dust operates on identical physics, but at cosmic distances, the consequences become absolute. Visible light, with wavelengths between roughly 0.4 and 0.7 micrometers, interacts violently with micrometer-sized dust grains. Photons get absorbed, scattered, deflected, and ultimately lost before they can traverse the vast dusty corridors separating distant stars from Earth. But infrared light tells a different story. Infrared wavelengths range from 1 micrometer to hundreds of micrometers, several times longer than the dust grains that destroy their visible counterparts. At these longer wavelengths, the same particles that obliterate visible light become feeble obstacles. Infrared radiation slips past them the way ocean swells roll over a pebble on the seafloor. At a wavelength of 2 micrometers, deep in the infrared spectrum, light penetrates interstellar dust roughly 10 times more effectively than blue light at half a micrometer. The curtain that blocks visible light becomes a semi-transparent veil when observed in infrared. The pioneers who learned to exploit this physics worked in an era when most astronomers still operated exclusively with visible light. Frank Lowe, working at the University of Arizona in the early 1960s, developed a germanium gallium bolometer sensitive enough to detect the faint infrared glow from celestial sources. His instrument cracked open a window that optical telescopes could never access. Through the following decades, infrared technology advanced from crude single-element sensors to sophisticated detector arrays capable of surveying millions of sources across the sky in a single observing run. The 2-micron all-sky survey, completed in 2001, scanned the entire celestial sphere at wavelengths near 2 micrometers, cataloging hundreds of millions of infrared sources invisible to optical instruments. The Spitzer Space Telescope, launched by NASA in 2003, carried infrared detectors beyond Earth's atmosphere, where water vapor and carbon dioxide could no longer absorb incoming signals. The Wide Field Infrared Survey Explorer, launched in 2009, extended this coverage further still, sweeping the full sky in multiple infrared bands from the clarity of orbit. Each successive mission peeled back another layer of cosmic fog, revealing stellar populations hidden behind galactic dust since the formation of the Milky Way itself. It was within this expanding infrared census that a cluster of stars emerged from behind one of the thickest dust screens in our galaxy. The cluster sits in the constellation Scutum, a small and easily overlooked pattern in the summer sky. Scutum lies in a direction that gazes straight toward the inner spiral arms of our galaxy, where stars crowd together in the densest concentrations visible from Earth. When you look toward Scutum on a clear summer night, the Milky Way appears thickest and brightest. But that visible richness conceals a deeper deception. The stars you see represent only the nearest layers of the galactic population. Behind them, curtain after curtain of dust blocks the light from vastly larger stellar communities buried deeper within the galactic interior. Charles Bruce Stephenson was an American astronomer at the Warner and Swayze Observatory, affiliated with Case Western Reserve University in Cleveland, Ohio. In 1990, he published a systematic catalog of bright infrared sources detected across the Milky Way. His work was methodical, careful, and deliberately restrained. Stephenson recorded what his instruments found without claiming to understand the physical nature of every source he documented. The infrared detectors available in 1990 lacked the sensitivity and resolution needed to determine whether a bright infrared point represented a single luminous star, a tight cluster of ordinary stars, or something entirely unrecognized. His catalog entry for a particular grouping of infrared sources in scutum represented one line among thousands. He labeled it Stephenson 2. Nobody understood what monsters that entry contained. The cluster Stephenson 2 holds at least 26 red supergiant stars, 26 dying giants crowded into a single gravitationally bound system, making it one of the most massive stellar clusters identified in our galaxy. The total mass of the cluster reaches somewhere between 40,000 and 100,000 solar masses, distributed across several hundred stars of various sizes, along with associated gas and dust. The cluster spans roughly 6 light-years from one edge to the other. To place that in human terms, consider that the nearest star to our Sun, Proxima Centauri, lies 4.24 light-years away. The entire Stephenson 2 cluster would fit comfortably inside the gap between our solar system and our closest stellar neighbor. Yet within that relatively compact volume, 26 red supergiants and dozens of smaller companions burn through their nuclear fuel at rates guaranteeing spectacular deaths within the next few million years. Among those 26 giants, one star stands entirely apart. Stephenson 218, sometimes designated Stephenson 2 DFK1 in technical literature, possesses dimensions that challenge the boundaries of what stellar physics permits. At infrared wavelengths near 2 micrometers, where the dust that erases over 99.9999% of its visible light blocks only a small fraction of its infrared emission, this star shines as one of the most brilliant sources in the sky. The object that remains utterly invisible through any optical telescope becomes one of the most conspicuous in the infrared universe. That violent contrast between optical darkness and infrared brilliance immediately marks this source as something demanding closer investigation. But Stephenson 218 is not alone in its invisibility. It is merely the most dramatic example of a far larger truth. Hundreds of millions of stars scattered across the Milky Way will never register on any optical detector, regardless of how large or technologically advanced that detector becomes. The physics of dust scattering guarantees their permanent absence from visible light surveys. Our galaxy harbors an estimated 5 million red supergiant stars at any given moment. That number emerges from roughly 1 billion stars, massive enough to eventually enter the red supergiant phase, multiplied by the tiny fraction of total stellar lifetime that this brief dying phase occupies. Of those, 5 million astronomers have measured the sizes of perhaps a few thousand with enough precision to rank them meaningfully. That sample represents less than 0.1% of the total population. How many record-breaking giants hide behind dust clouds thicker than the one shielding Stephenson 218? How many clusters more extreme than Stephenson 2 remain uncatalogued in the uncharted inner regions of the galaxy? We cannot know until we look. Everything humanity understands about the cosmos depends on which kind of light we choose to collect. For millennia, our species possessed exactly one astronomical detector, the human eye, sensitive to a sliver of the electromagnetic spectrum between 400 and 700 nanometers. We built entire cosmologies around that narrow window and counted the visible stars and believed we had counted them all. Then, radio astronomy revealed quasars blazing at the edges of the observable universe. X-ray telescopes revealed black holes devouring companion stars in binary systems. Gamma-ray observatories revealed the most violent explosions since the origin of the universe. And infrared instruments revealed the largest known star, burning invisibly behind 20,000 light-years of cosmic dust in a constellation you can find on any summer evening, if you know where to look. Before the 4th of October, 1957, most Americans considered space a domain for science fiction and philosophical speculation rather than engineering. Then a polished metal sphere, weighing 184 pounds, began orbiting Earth, transmitting a steady beep that amateur radio operators across the country could receive on ordinary equipment. Sputnik carried no scientific instruments of consequence. Its power lay entirely in what it proved possible. The barrier between Earth and orbit was not impenetrable. It simply required the right tool to breach. Every new wavelength of light that astronomers learn to collect is a Sputnik moment for human perception. Each one demolishes a wall we did not know existed and reveals a universe larger, stranger, and more populated than the one visible through the previous window. We do not see the cosmos as it is. We see the fraction that our instruments currently permit. But knowing that Stephenson 218 exists behind its curtain of dust is only the first step. The real challenge dwarfs the discovery itself. Measuring the precise dimensions of an object 20,000 light-years away that no human eye can detect requires techniques that push observational astronomy to its absolute limits. The task resembles trying to determine the diameter of a single coin sitting in a city on the opposite side of Earth, using nothing but faint infrared light filtering through fog. The coin analogy is not hyperbole. It captures the fundamental difficulty that confronts every astronomer attempting to measure stellar sizes across interstellar distances. On Earth, measuring the dimensions of an object requires nothing more exotic than proximity and a reliable instrument. A ruler pressed against a tabletop, a laser rangefinder bounced off a building facade, a radar pulse timed against the speed of light. These methods share a common luxury. The object being measured sits close enough to interact with directly. Stars deny us that luxury entirely. Stephenson 218 burns roughly 20,000 light-years from Earth. Light itself, the fastest phenomenon permitted by the laws of physics, requires 20,000 years to cross that gap. The photons arriving at our telescopes tonight departed the star around the time human ancestors were crossing the Bering Land Bridge into the Western Hemisphere, carrying stone tools and wearing animal hides, with no written language, no agriculture, no cities anywhere on the planet. Every measurement we make of this star is a measurement of the ancient past, encoded in radiation older than civilization itself. At that distance, even an object of staggering physical dimensions shrinks to an angular size so small that it defies the resolving power of virtually every telescope in existence. To grasp how small, you need to understand the unit astronomers use to describe such measurements. An arcsecond represents 1/3600th of a single degree. The full moon, hanging large and luminous in the night sky, spans roughly 1,800 arcseconds across. A human hair held at arm's length covers approximately 60 arcseconds of sky. These are measurements the human visual system can process without strain. Stars at cosmic distances occupy an entirely different regime. Their angular diameters collapse into milli-arcseconds, thousandths of an arcsecond, or even micro-arcseconds, millionths of an arcsecond. Stephenson 218. Despite possessing a physical diameter approaching 2 billion miles, subtends an angle so minuscule at 20,000 light-years that it appears as nothing more than a dimensionless point of infrared light. No telescope, no matter how large its mirror or how precise its optics, can simply zoom in and see the disk of this star the way you might see the disk of the moon through binoculars. The angular size falls below the resolving threshold of every individual instrument ever constructed. This is the wall that stellar measurement collides against, and overcoming it requires not one technique, but two, executed in sequence, each introducing its own layer of uncertainty that compounds the difficulty at every step. The first technique determines how large the star appears from our vantage point, a quantity called angular diameter. Since no single telescope can resolve the stellar disk directly, astronomers employ a method called interferometry. The principle is elegant and, once understood, almost intuitive. A single telescope has a resolving power limited by the diameter of its mirror. Larger mirrors resolve finer details. But building mirrors beyond a certain size becomes physically and financially prohibitive. Interferometry circumvents this limit by combining the light collected from two or more telescopes. Separated by a considerable distance, the combined signal behaves as though it came from a single telescope with a mirror diameter equal to the separation between the individual instruments. Two telescopes placed 100 meters apart achieve the resolving power of a single mirror 100 meters across, an instrument that could never be physically constructed, but whose resolution can be synthetically replicated. Think of it the way human hearing works. A single ear can detect sound, but two ears separated by the width of your skull allow your brain to pinpoint the direction of that sound with far greater precision than either ear alone. Interferometry gives telescopes the same advantage. Two instruments separated in space hear the light with a directionality that neither possesses individually. Infrared interferometers operating at wavelengths near 2 micrometers can resolve angular sizes in the milli-arcsecond range, sufficient to constrain the apparent diameters of even distant red supergiants. But this measurement, however precise, tells you only how large the star appears from Earth, and apparent size is a deception that the universe exploits mercilessly. A small star orbiting nearby and a colossal star burning at enormous distance can project identical angular sizes onto the sky. Without knowing which scenario applies, the angular diameter measurement is meaningless. Converting apparent size into actual physical dimensions requires a second, entirely independent measurement: distance. The primary method astronomers use to determine stellar distances is called parallax, and it relies on the oldest trick in spatial perception. Hold your thumb in front of your face and close one eye. Then switch eyes. Your thumb appears to shift position against the background because your two eyes observe it from slightly different locations. The closer the thumb, the larger the apparent shift. Move it to arm's length and the shift is modest. Bring it close to your nose and the shift becomes dramatic. Parallax exploits this same geometry on a cosmic scale. As Earth orbits the Sun, it shifts position by roughly 186 million miles over the course of 6 months, moving from one side of its orbit to the opposite side. A nearby star observed in January and again in July will appear to shift slightly against the background of far more distant stars. The size of this shift, measured in arcseconds, relates directly and mathematically to the star's distance. Smaller shifts indicate greater distances. The relationship is clean, geometrically exact, and requires no assumptions about the star's physical properties. Pure triangulation applied across interstellar space. The challenge lies entirely in precision. Stars beyond a few hundred light-years show parallax shifts so tiny that ground-based measurements struggle to capture them reliably. Atmospheric turbulence blurs stellar positions by amounts comparable to or larger than the parallax signal itself. For decades, this limitation capped accurate parallax distances at a few hundred light-years, leaving the vast majority of the galaxy's stellar population beyond reach. The European Space Agency shattered that barrier. In December of 2013, it launched the Gaia spacecraft into orbit at the second Lagrange point, roughly 1 million miles from Earth, where the spacecraft circles the Sun in gravitational lockstep with our planet. Free from atmospheric distortion, Gaia measures stellar positions with a precision approaching micro-arcseconds, roughly 1,000 times better than the best ground-based observations. Over years of continuous scanning, the spacecraft has tracked the positions of nearly 2 billion stars, recording their tiny parallax wobbles as Earth and Gaia together orbit the Sun. The resulting distance catalog represents the most comprehensive three-dimensional map of the Milky Way ever assembled. for Stephenson 218, combining Gaia's distance estimate with interferometric angular diameter measurements and sophisticated atmospheric models developed by theoretical astrophysicists. The converging calculations produced a figure that seemed almost impossible when first reported. Stephenson 218 measures approximately 2,150 solar radii in diameter. The uncertainty ranges from roughly 1,800 to 2,400 solar radii, depending on methodology and the specific research group performing the analysis. But even the most conservative boundary of that range places this star among the largest objects ever identified in the observable universe. Let me translate that measurement into terms that human perception might attempt to process. Though I offer the honest warning that intuition will collapse regardless of how carefully the comparisons are constructed. Our sun measures roughly 865,000 miles across. This already exceeds meaningful comprehension. You could line up 109 Earths across the sun's diameter. The sun contains enough volume to hold 1.3 million Earths inside it. By every standard that governs daily human experience, our star is enormous. Stephenson 218 dwarfs it by a factor that erases the meaning of the word enormous. The diameter of Stephenson 218 reaches approximately 2 billion miles. Written as a single number, that figure requires 10 digits. Light itself, the fastest thing in the universe, traveling at 670 million miles per hour, requires more than 8 hours to complete a single circuit around the equator of this star. Consider the comparison directly. Light travels from the sun to Earth in 8 minutes and 20 seconds. That same light needs over 8 hours merely to wrap once around Stephenson 218. A commercial airplane cruising at 500 miles per hour would need more than 400,000 years to cross the diameter. If that flight had departed when anatomically modern humans first appeared in Africa, it would still face hundreds of thousands of years of travel before reaching the far edge. The journey would span more generations than have existed in the entirety of human history. But diameter captures only one dimension of this object. Volume scales with the cube of radius, a mathematical relationship that amplifies size differences with devastating multiplying force. When you double the diameter of a sphere, you increase its volume not by a factor of 2, but by a factor of 8. When you increase diameter by a factor of 2,150, the volume increases by approximately 10 billion. Nearly 10 billion suns could fit inside Stephenson 218 with room remaining. If our sun were the size of a standard basketball, roughly 9.5 inches across, then Stephenson 218 would be a sphere approximately 1,700 feet in diameter. That exceeds the height of the Empire State Building. A basketball resting on a table compared to a sphere taller than the most famous skyscraper in Manhattan. That is the volume ratio between the star that sustains all life on Earth and the largest known star in the universe. Now, place this object inside our solar system. Set the core of Stephenson 218 at the exact position where our sun currently burns. Its surface expands outward, swallowing everything it encounters. Mercury disappears, vaporized inside the stellar interior. Venus disappears. Earth and every human being who has ever drawn breath disappears. Mars and every robotic explorer we have landed on its surface disappears. The entire asteroid belt. Millions of rocky fragments orbiting between Mars and Jupiter. Disappears. Jupiter, the largest planet in our solar system, a world massive enough to contain all other planets combined, disappears along with its 95 known moons. Saturn, with its magnificent ring system spanning distances greater than the diameter of Earth, would orbit just above the churning surface of this stellar monster, occasionally grazing the outermost atmosphere during the closest approaches of its elliptical path. Uranus and Neptune would survive. But from Uranus, the sky would no longer resemble anything a human mind could interpret as normal. A dim red wall of light would stretch from horizon to horizon, covering half the celestial sphere. The concept of daytime would lose its meaning entirely. Day and night, as every organism on Earth has ever known them, require a sun that occupies a small point in the sky. When your sun fills half your visual field, the distinction between illuminated and dark simply ceases to exist. Yet here, the data delivers its sharpest twist, and it cuts against everything the preceding numbers seem to demand. This object that swallows the orbit of Saturn, that contains the volume of 10 billion suns, possesses an average density lower than the best vacuum any laboratory on Earth has ever achieved. The arithmetic is straightforward. Stephenson. 218 currently retains an estimated 15 to 25 solar masses. Most of the material it was born with has already been stripped away by stellar winds over hundreds of thousands of years. Divide that modest remaining mass by a volume 10 billion times greater than the Sun, and the average density plummets to approximately 1/10 billionth of the Sun's average density. Our Sun averages roughly 1.4 grams per cubic centimeter, slightly denser than liquid water. 1/10 billionth of that value produces a number so small it loses all physical intuition. Earth's atmosphere at sea level has a density of roughly 1/1000th of a gram per cubic centimeter. The average interior of Stephenson 218 is approximately 10 million times less dense than the air you are breathing at this moment. A cubic meter scooped from a random location inside this star would contain less matter than a cubic meter of interplanetary space within our solar system. You could fly through the vast majority of this object and encounter almost nothing at all, drifting through a thin haze stretching across billions of miles, less substantial than the finest mist that has ever settled over a mountain valley at dawn. The human brain evolved to process a world built on scales between a grain of sand and a mountain peak, roughly 6 orders of magnitude. Everything smaller than a cell or larger than a continent exists beyond the hardware our biology provides. We do not truly comprehend 10 billion. We manipulate symbols on a page and trust the mathematics. Millions of Americans sat before flickering black and white television screens in July of 1969, watching a ghostly figure descend a ladder onto the lunar surface, and they had to trust that the grainy image represented a real human being actually walking on another world 240,000 miles away. Sometimes reality exceeds the capacity of direct experience, and faith in method is all we have. The numbers describe what Stephenson 218 is. They do not explain why. To understand how a star can inflate to dimensions that mock the scale of entire planetary systems, we must rewind 20 million years to the moment this object was born, not as the bloated red monster we observe today, but as a compact blue furnace hundreds of times smaller and thousands of degrees hotter. Every driver understands a simple truth about fuel and distance. A larger gas tank carries you further down the highway. Double the tank, double the range. The logic is so intuitive that it barely qualifies as reasoning. It feels more like common sense, the kind of principle that children grasp before they learn to read. Apply this logic to stars and a reasonable prediction emerges. Our sun contains enough hydrogen fuel to sustain nuclear fusion for approximately 10 billion years. It has already burned through roughly half that supply, with another 5 billion years of stable energy production ahead. A star born with 30 times the sun's mass should carry 30 times the fuel, 300 billion years of steady burning, an almost immortal furnace outlasting the current age of the universe 20 times over. The prediction is perfectly logical. It is also perfectly wrong. A star 30 times more massive than our sun exhausts its hydrogen in roughly 10 to 15 million years. Not 300 billion, not even 1 billion. 15 million at the outside, a lifespan shorter than the sun's by a factor of nearly 1,000. The star with 30 times more fuel dies 1,000 times sooner. The universe operates on principles that punish intuition at every scale. And nowhere is the punishment more brutal than in the relationship between stellar mass and stellar lifetime. The explanation lies in temperature, and temperature's savage relationship with nuclear reaction rates. Imagine two bank accounts. One belongs to a schoolteacher earning a modest salary, spending carefully, stretching every dollar across decades. The other belongs to a billionaire whose wealth dwarfs the teacher's by a factor of 1,000, but whose spending habits outpace the teacher's by a factor of 1,000,000. The billionaire burns through a fortune that took generations to accumulate in a few reckless years. Massive stars are the billionaires of the cosmos. They possess more fuel, but they squander it at rates so extreme that no surplus can compensate. The physics behind this profligacy centers on the stellar core. More massive stars generate stronger gravitational fields, compressing their cores to higher densities and temperatures. During its main sequence phase, the core of Stephenson 218 reached temperatures exceeding 40 million Kelvin, roughly 3 times hotter than the Sun's core temperature of 15 million Kelvin. This difference sounds modest, a factor of 3. But nuclear fusion rates do not scale linearly with temperature. They scale exponentially. The dominant hydrogen fusion process in massive stars differs fundamentally from the one operating inside our Sun. The Sun fuses hydrogen through the proton-proton chain, a relatively slow sequence in which individual protons collide and combine step by step. Massive stars bypass this sluggish pathway entirely. They employ the carbon-nitrogen-oxygen cycle, a process that uses carbon, nitrogen, and oxygen nuclei as catalysts, passing hydrogen nuclei through a series of reactions that ultimately produce helium far more rapidly than the proton-proton chain ever could. The reaction rate of the carbon-nitrogen-oxygen cycle scales approximately with the 16th power of temperature. The 16th power. If you double the core temperature, the reaction rate increases by a factor of 2 raised to the 16th power, which is 65,536. A modest increase in temperature unleashes an enormous increase in fuel consumption. This relationship drives the mass-luminosity connection that governs every star in the universe. Double a star's mass, and its luminosity increases by roughly a factor of 10 or more. The fuel supply grows proportionally with mass, but the rate of consumption grows as a steep power law, climbing far faster than the supply can keep pace. Massive stars do not simply burn brighter. They burn with an extravagance that guarantees an early death. They are born with larger inheritances and spend them at rates that ensure bankruptcy in a cosmic eye blink. Before we trace what happens when that bankruptcy arrives, hold the timeline of Stephenson 218's life against a human calendar. If the hydrogen burning phase, lasting roughly 12 million years, were compressed into a single calendar year, beginning on January 1st, then the helium burning phase that follows would occupy roughly half a day. Carbon burning would last 45 seconds. Neon burning would flash past in 3 seconds. Oxygen burning would consume a single second. And silicon burning, the final act before catastrophe, would fill 1/100th of a second, a duration so brief that the human nervous system could not register its beginning before it ended. The star spends nearly its entire existence in the first stage, then hurtles through every subsequent chapter with accelerating desperation, each phase shorter than the last by orders of magnitude. This is the countdown that every massive star follows. And it is already well underway inside Stephenson 218. When hydrogen fusion first ignited in the core of this star roughly 20 million years ago, the object that emerged bore no resemblance to the bloated red giant we observe today. The young Stephenson 218 shone as a brilliant blue supergiant. Surface temperatures exceeded 20,000 Kelvin, more than 3.5 times hotter than the surface of our Sun. the star radiated primarily in ultraviolet wavelengths, pouring out energy lethal to any biological chemistry within light years of its position. Any planet orbiting nearby would have been bathed in sterilizing radiation that would dismantle organic molecules before they could form anything resembling a cell. This was a compact furnace, perhaps 10 to 20 times the Sun's radius, dense with energy, radiating at rates tens of thousands of times greater than our star per unit of volume. Throughout this main sequence phase, lasting approximately 12 million years, the star maintained a state that physicists call hydrostatic equilibrium. Two forces waged perpetual war across every layer of the stellar interior. Gravity pulled every particle inward, attempting to crush the star into its own center. The weight of the overlying material pressed down on every deeper layer, compounding the inward force at every depth, left unopposed. Gravity would collapse the entire object into a point of infinite density within minutes. But gravity was not unopposed. Nuclear reactions in the core released energy that traveled outward through the stellar interior as radiation, pushing against the infouling material with a pressure that exactly matched the gravitational force at every point. Neither side won. Neither side could win. The star hung suspended in a balance so precise that it persisted unchanged across millions of years. Like two evenly matched teams locked in a tug of war, the rope motionless between them, neither side yielding a single inch. The equilibrium held for as long as fuel remained available to power the outward push. But fuel does not last forever, no matter how vast the initial supply. Hydrogen fusion converts 4 hydrogen nuclei into 1 helium nucleus, releasing energy equivalent to the tiny mass difference between the reactants and the product through the relationship described by Einstein's famous equivalence of mass and energy. Roughly 0.7% of the original hydrogen mass transforms into pure energy during each reaction. The helium produced accumulates in the core like ash, building up in a fireplace. And like ash, it contributes nothing to the fire. Helium nuclei carry greater positive electrical charge than hydrogen nuclei, repelling each other more forcefully. Temperatures exceeding 100 million Kelvin are required before helium nuclei can approach closely enough for the strong nuclear force to seize them and fuse them together. The core during hydrogen burning runs far too cool for helium ignition, so the helium sits, inert, accumulating, growing heavier with each passing millennium as fresh hydrogen converts into fresh waste. The core gradually transforms from a functioning reactor into a ball of nuclear ash, still crushingly dense, still blisteringly hot, but producing nothing. The hydrogen available for fusion retreats into an ever thinner shell surrounding the growing helium core, like a fire burning around the edges of its own ash pile. When the last hydrogen in the core is consumed, the equilibrium that sustained the star for 12 million years breaks catastrophically. The outward push vanishes. Gravity, patient and relentless, meets no resistance. The helium core begins to contract, falling inward under its own weight. This contraction converts gravitational potential energy into thermal energy, heating both the core and the surrounding layers. A thin shell of hydrogen just outside the core reaches temperatures sufficient to ignite fusion, creating a new burning zone wrapped around the inert helium center like a ring of fire surrounding a cooling ember. This shell-burning phase produces more energy than the original core fusion ever did. The paradox seems impossible. Less fuel burning in a thinner zone somehow generates greater total output. But the shell burns at higher temperatures and greater densities than the original core, accelerating reaction rates beyond what the previous configuration achieved. The enormous energy flowing outward from this shell pushes against the outer layers of the star with a force that exceeds anything the star experienced during its main sequence lifetime. The outer layers respond by expanding. The surface retreats outward against gravity, swelling across distances measured in hundreds of millions of miles. As the material spreads across ever larger volumes, it cools. The surface temperature drops from the searing blue-white of 20,000 Kelvin toward the deep red of 3 to 4,000 Kelvin. The compact blue furnace transforms into a bloated red sphere over timescales of thousands of years, brief by stellar standards, still longer than any human civilization has existed. Inside this expanding envelope, the helium core continues contracting and heating. When the core temperature reaches approximately 100 million Kelvin, helium ignites through a reaction called the triple alpha process. The name describes what happens with clinical precision. 3 helium nuclei, each called an alpha particle in physics terminology, must combine nearly simultaneously to produce a single carbon-12 nucleus. The process unfolds in 2 absurdly improbable steps. 2 helium nuclei collide and briefly form beryllium-8, a nucleus so unstable that it decays back into 2 helium nuclei within approximately 10 to the negative 16th power of a second, a time interval so short that light itself travels less than the width of an atom. Yet within that vanishing window, a 3rd helium nucleus must strike the beryllium-8 before it disintegrates, forming stable carbon-12. The probability of this occurring in any single collision is extraordinarily small. But at 100 million Kelvin, the number of collisions occurring every second in every cubic centimeter of the core is so astronomically large that the improbable becomes routine. Helium burning sustains the star for roughly 1 million years before the helium supply exhausts itself, leaving behind a core of carbon and oxygen that contracts further under gravity. Now, the star carries a helium-burning shell surrounding an inert carbon-oxygen core, with a hydrogen-burning shell farther out, and the vast convective envelope stretching to the distant photosphere. Carbon ignites when core temperatures approach 500 million Kelvin, fusing into neon and magnesium over roughly 1,000 years. Neon burns in a few years. Oxygen burns in a few months. Silicon burns in 1 to 2 days. Each phase deposits heavier elements into the center, while lighter elements continue burning in concentric shells surrounding the core. The star develops the layered architecture of an onion sliced in half, iron and nickel at the innermost center, surrounded by silicon, then oxygen, then neon, then carbon, then helium, then hydrogen. Each shell a separate nuclear furnace operating at different temperatures, different densities, consuming different fuel, all nested within one another like the rings of a target. And here the data delivers a twist that transforms this stellar biography from remarkable to surreal. The surface of Stephenson 218, that dim red photosphere nearly 2 billion miles from the center, has no knowledge of what is happening in the core. Sound waves and stellar material travel at speeds governed by local temperature and density. In the tenuous outer layers of this star, sound moves at roughly a few kilometers per second. Given the immense diameter, acoustic signals require weeks to travel from one side to the other. The information about current core conditions has not yet reached the photosphere. The surface we observe tonight reflects conditions from years or decades ago. The core may have already entered silicon burning. It may have already exhausted its silicon and begun accumulating iron. It may have already collapsed. The surface would not yet know. The star operates as a disconnected system. The core races through its final nuclear stages with escalating urgency, while the envelope floats serenely above, unaware that the engine driving its existence is about to fail. Arthur Eddington laid the mathematical foundations of stellar structure theory at Cambridge in the 1920s, establishing the equations that govern how pressure, temperature, density, and energy transport interact within stars. Those same equations describe both our modest sun and the monstrous interior of Stephenson 218. The same fundamental laws, the same physics. Only the initial conditions differ. The founding fathers drafted one constitution, That single document, applied across different eras with different populations under different pressures, produced periods of American life so distinct they barely resemble one another. The rules remain constant. The outcomes diverge wildly depending on starting conditions. Stars obey this principle with mathematical precision. Change the initial mass, and every subsequent chapter of the story rewrites itself entirely. The star has swollen. It has cooled. It has become the largest known object of its kind in the observable universe. But the surface of this monster harbors strangeness beyond anything that size alone can explain. A place where molecules form in the atmosphere of a star, where stellar winds strip away mass equivalent to our entire sun every few thousand years, where the boundary between star and empty space dissolves into a gradient so gradual that the question of where one ends and the other begins has no definitive answer. Every photograph of our sun reinforces the same violent imagery. Towering arcs of superheated plasma erupting thousands of miles above the surface. Dark sunspots, larger than Earth, swirling with magnetic fury. Coronal mass ejections hurling billions of tons of charged particles into space at millions of miles per hour. NASA's Solar Dynamics Observatory has delivered these images in stunning resolution since 2010. And they have cemented a picture of stellar surfaces as places of ferocious heat and blinding intensity. The natural assumption follows without effort. A star 2,150 times wider than the Sun must possess a surface proportionally more extreme, hotter, brighter, more violent in every measurable dimension. The assumption collapses on contact with the data. The surface temperature of Stephenson 218 hovers around 3,200 Kelvin. Our Sun's surface reaches 5,778 Kelvin. A blue supergiant like Rigel in Orion exceeds 11,000 Kelvin. Stephenson 218, the largest known star in the observable universe, runs cooler than every star you can identify with the naked eye on a clear winter night. Its surface temperature falls nearly 45% below the Sun's. And that reduced temperature produces a consequence that seems to contradict the very definition of what a star should be. Molecules form on the surface of Stephenson 218. Not atoms, molecules. Complex bonded structures involving multiple atoms joined by shared electrons. Spectroscopic observations detect titanium oxide, water vapor, and carbon monoxide in the outer atmosphere of this star. Titanium oxide would be annihilated instantly at the Sun's surface temperature, its molecular bonds shattered by thermal energy, far exceeding the bond strength holding the atoms together. Water vapor cannot survive 5,700 degrees. Carbon monoxide dissociates into its constituent atoms thousands of degrees below solar surface conditions. Yet on Stephenson 218, these molecules persist, absorb starlight at characteristic wavelengths, and imprint their signatures onto the spectrum that reaches our telescopes. The titanium oxide bands, in particular, give red supergiants their distinctive color and spectral classification. Without these molecules, the star would look different, behave differently in our instruments, and prove far more difficult to characterize. Chemistry operates on the surface of a star. The sentence reads like a contradiction. It is not. It is a direct consequence of size. The physics connecting temperature, size, and total luminosity follows a relationship that the Austrian physicist Josef Stephan described in 1879 and his student Ludwig Boltzmann derived theoretically in 1884, stated in plain language rather than equations. The principle says this: the total energy a star radiates depends on two factors multiplied together. The first is surface temperature, raised to the fourth power. The second is the total surface area. A star twice as hot radiates 16 times more energy per unit area, but a star with twice the radius has 4 times the surface area, and a star with 2,000 times the radius has 4 million times the surface area. Stephenson 218 sits on the cold side of this relationship. Each square meter of its photosphere emits significantly less energy than each square meter of the Sun's photosphere, because the temperature is lower and the fourth power dependence amplifies that difference dramatically. But the surface area of Stephenson 218 exceeds the Sun's by a factor greater than 4 million. The total output, the product of weak emission per unit area multiplied by a staggering number of unit areas, reaches somewhere between 440,000 and 630,000 times the Sun's luminosity. Think of it as a comparison between two light sources. A single 10-watt bulb glowing intensely on a desk produces a concentrated pool of bright light. A 5-watt bulb glows dimmer at every point, but cover every surface of a football stadium with 5-watt bulbs, millions of them, and the combined output of that stadium overwhelms the single desk lamp by orders of magnitude. Stephenson 218 is the stadium. Our Sun is the desk lamp. Each point on the stadium's surface glows fainter, but the total real estate producing light defies comparison. The reduced surface temperature shifts the peak of the star's emission to longer wavelengths, a consequence of the principle Wilhelm Wien formulated in 1893. Hotter objects radiate most intensely at shorter wavelengths. The Sun, at 5,778 Kelvin, peaks in the visible range near yellow-green. A star at 3,200 Kelvin peaks near 2 micrometers, deep in the infrared spectrum, well beyond the range of human vision. Stephenson 218 is naturally an infrared object. Even without a single grain of interstellar dust between it and Earth, this star would still shine brightest at wavelengths our eyes cannot detect. The dust that hides it from optical telescopes merely compounds an invisibility that the star's own physics already guarantees. Standing on a hypothetical planet orbiting this star, you would confront a visual experience for which no earthly analogy fully prepares you. A wall of dim red light would fill half the sky, stretching from one horizon to the other, covering the entire hemisphere above you with a faintly glowing surface. Each square meter of that surface radiates less intensely than each square meter of our Sun. The light would not blind you the way staring at the Sun from Earth would. Instead, the sky would resemble an eternal twilight, a sunset that never ends, painted across half the universe in a deep somber crimson. The total energy pouring down onto your planet would be catastrophic, enough to sterilize any biosphere. But the quality of the light, its character, would feel dim rather than fierce. An ocean of faint red warmth reaching you from every direction at once, inescapable not because of its intensity, but because of its sheer coverage. The strangeness deepens when you ask the most basic question about any physical object. Where does it end on Earth? Boundaries feel absolute. A coastline separates land from water. A wall separates inside from outside. Even the atmosphere possesses a definable upper limit where air becomes too thin to measure. We navigate a world of edges, borders, and sharp transitions. The surface of a red supergiant obeys none of these conventions. The photosphere, the layer astronomers designate as the stellar surface, is defined as the depth at which the star becomes opaque to its own radiation. Below the photosphere, photons cannot escape freely. They scatter, absorb, re-emit, and random walk through dense material. Above the photosphere, photons stream outward into space with minimal further interaction. This transition from opaque to transparent defines the visible surface of any star. For the Sun, the photosphere is relatively well defined. The transition occurs across a layer only a few hundred kilometers thick, a sharp boundary compared to the Sun's total radius of nearly 700,000 kilometers. The edge is not mathematically perfect, but it is crisp enough that solar photographs show a distinct limb, a clear circular border separating star from sky. For Stephenson 2:18, the photosphere is something else entirely. The density at this boundary drops to roughly 1/1000th of Earth's atmospheric density at sea level. 1/1000th. High vacuum chambers used in physics laboratories on Earth typically achieve densities millions of times higher than this. The material forming the visible surface of the largest known star would qualify as a better vacuum than most instruments on Earth can produce. You would not stand on this surface. You would not feel it. You would drift through it like a spacecraft, passing through the outermost wisps of a comet's tail, detecting almost nothing. Yet this impossibly tenuous material produces the light we observe. Photons generated in deeper, denser regions scatter and absorb through this extended atmosphere before finally escaping into space. The long path through low-density gas allows even weak absorption processes to modify the emerging radiation significantly. The star has no edge. It fades. It thins. It dissolves gradually from something that might generously be called a stellar atmosphere into something indistinguishable from the vacuum of interstellar space. Where the star ends and space begins is a question of definition, not physics. This object without a fixed boundary also lacks a fixed size. Stephenson 2:18 breathes. Red supergiants pulsate, expanding and contracting over cycles lasting hundreds to thousands of days. The mechanism driving this oscillation operates through a feedback loop, connecting temperature, opacity, and pressure. When the outer layers compress slightly, the compression heats the gas. In certain temperature ranges, hotter gas becomes more opaque, meaning it blocks radiation more effectively. The trapped radiation increases the local pressure, which drives the material outward again. As the layers expand, they cool. Cooling reduces opacity. The trapped radiation escapes. Pressure drops. Gravity pulls the material back inward. The cycle repeats. The physics resembles the operation of a steam engine. Opacity acts as a valve, alternately trapping and releasing energy, converting thermal fluctuations into mechanical oscillation with remarkable regularity. For Stephenson 2:18, the pulsation period probably spans several years, consistent with its enormous dimensions and low average density. During maximum expansion, the star might exceed 2,200 solar radii. During minimum contraction, it might shrink below 2,000, a variation of 10% or more in radius, corresponding to a change greater than 30% in total volume. The largest known star does not hold still. It swells and contracts in a slow cosmic rhythm, its size at any given moment, depending on where it sits within its breathing cycle. While the star breathes, it bleeds. 3 separate mechanisms strip mass from Stephenson 2:18 simultaneously, each operating through different physics, each contributing to a hemorrhage that dwarfs anything occurring in our solar system. The first mechanism is dust-driven wind. As the extended atmosphere expands and cools beyond the photosphere, temperatures in the outermost regions drop below roughly 1,500 Kelvin. At these temperatures, silicate and carbon-rich dust grains condense directly from the gas phase, assembling atom by atom the way frost crystallizes on a cold window. These dust grains absorb starlight with brutal efficiency. The radiation pressure from the star accelerates them outward. The accelerating grains collide with surrounding gas molecules, dragging the gas along. A continuous stellar wind flows outward, carrying mass away from the star at velocities of 10 to 30 kilometers per second. The second mechanism is shock-driven ejection. When the star contracts during its pulsation cycle, the compression propagates outward as a pressure wave. As this wave travels through the steeply declining density profile of the outer atmosphere, it steepens into a shock front. The shock accelerates pockets of gas to velocities exceeding the local escape speed, launching discrete shells of material into space. Each pulsation cycle ejects another shell, The process repeats every few years, building up layers of previously expelled material at progressively greater distances from the star. The third mechanism is convective lifting. The enormous convection cells operating in the outer envelope transport hot gas upward from deeper layers. Some of this material reaches altitudes where the gravitational binding energy is so weak that even modest additional velocity allows escape. The surface gravity of Stephenson 218 is roughly 100,000 times weaker than Earth's surface gravity. Material elevated by convection to the outermost atmospheric layers needs only a gentle push to leave the star permanently. The combined mass loss rate from all three mechanisms is staggering. Stephenson 218 sheds the equivalent of the Sun's entire mass every few thousand to 10,000 years. For comparison, the solar wind carries approximately 1 million tons of material away from the Sun every second. The mass loss from Stephenson 218 exceeds this by factors of billions. The expelled material, traveling outward at 10 to 30 kilometers per second, forms concentric shells of gas and dust surrounding the star at various distances, each glowing faintly in infrared light as the dust grains absorb stellar radiation and re-emit at longer wavelengths. Each shell records a particular era of mass loss, frozen at the distance it has reached since ejection. Dense shells mark periods of vigorous expulsion. Gaps between shells mark quieter intervals. The pattern reads like tree rings, encoding thousands of years of stellar history in the distribution of circumstellar debris. Sound itself behaves strangely in an object this large. Acoustic waves in the tenuous outer layers of Stephenson 218 travel at only a few kilometers per second. At this speed, a sound wave would require weeks to cross from one side of the star to the other. No signal propagating through the stellar interior can coordinate the behavior of distant regions on any timescale relevant to observation. The left side of the star does not know what the right side is doing. The photosphere cannot communicate with the core. The star is too large to know itself. Watson and Crick published The Structure of DNA in 1953, and their discovery launched decades of investigation into where the boundary between living and non-living matter actually falls. Viruses possess genetic material and replicate, yet lack metabolism and cannot reproduce independently. Prions propagate without any genetic material at all. The sharp line between life and non-life that seemed obvious before molecular biology turned out to be an artifact of limited resolution. The closer scientists looked, the more the boundary blurred into a gradient. Nature draws very few hard lines. The categories we impose, living or dead, star or space, surface or vacuum, often say more about the limitations of human language than about the structure of reality. Stephenson 218 breathes, bleeds, and dissolves into the void around it. It possesses no fixed size, no sharp edge, and a surface less substantial than the emptiest vacuum chambers on Earth. But it remains the largest known star, and the question of whether that distinction is truly secure, whether some rival lurks behind even thicker dust or within some uncharted cluster, has fueled a decades-long contest among the most extreme objects in our galaxy. A contest with a history of shifting crowns, revised measurements, and surprises that have repeatedly rewritten the rankings. For most of the first decade of the 2000s, the answer to the question which star is the largest in the universe carried a single name: VY Canis Majoris. It appeared in Discovery Channel documentaries narrated by deep authoritative voices. It surfaced in National Geographic specials and classroom presentations, and the kind of hardcover astronomy books that ended up as Christmas gifts for curious grandchildren. VY Canis Majoris dominated popular science discussions of stellar extremes with a persistence that transformed it from a scientific finding into a cultural fact. If you followed space science at all during those years, you knew the name. You accepted it the way you accepted that Everest was the tallest mountain and the Mariana Trench was the deepest point in the ocean. Settled. Permanent. Beyond revision. That certainty was misplaced. It was always misplaced. The title of largest known star is not a fixed monument carved into the bedrock of astronomy. It is a moving target, hostage to the precision of the instruments making the measurements and the accuracy of the distance estimates underpinning every calculation. Improve the instruments and the rankings shift. Revise the distances and the record holders shuffle. The history of this contest reads less like a stable leaderboard and more like a decades-long reshuffling, where each advance in technology dethrones one champion and elevates another. VY Canis Majoris burns approximately 3,900 light-years from Earth in the constellation Canis Major. Visible from the southern hemisphere and much of the northern, early size estimates placed this star near 2,000 solar radii, a figure that earned it the crown and the fame that followed. The star is undeniably spectacular. Hubble Space Telescope images reveal a complex circumstellar environment of arcs, knots, and filaments. Material ejected by the star's ferocious mass loss over thousands of years. The structures surrounding VY Canis Majoris look like the aftermath of a slow-motion explosion frozen in mid-flight, sculpted by radiation pressure and stellar winds into shapes that astrophotographers prize for their beauty and complexity. But beauty does not determine size, and the numbers that once made VY Canis Majoris the undisputed champion did not survive closer scrutiny. Subsequent analyses by multiple research groups, including detailed work by Witkowski and collaborators using interferometric techniques at the Very Large Telescope in Chile, revised the star's dimensions significantly downward. Improved distance measurements from the Gaia spacecraft suggested the star sits somewhat closer than original estimates assumed. When you reduce the distance to a star while holding its angular diameter constant, the calculated physical size shrinks proportionally. The most comprehensive modern assessments place VY Canis Majoris at approximately 1,400 to 1,500 solar radii. Still enormous by any standard. Still a red supergiant of extraordinary proportions, but clearly and measurably smaller than Stephenson, 218. The gap between the two stars exceeds the diameter of our entire sun many times over. UY Scuti presented a more direct challenge. Located approximately 5,700 light-years from Earth, also in the constellation Scutum, and tantalizingly close to Stephenson, 2 on the sky. UY Scuti entered the record books with initial size estimates reaching 1,700 to 2,000 solar radii. For a period, some references listed it as the largest known star, rivaling or exceeding the upper bounds claimed for Stephenson, 218. The competition appeared genuinely contested. Then, Gaia delivered updated distance measurements. UY Scuti turned out to lie somewhat closer than original calculations assumed. The same geometric logic that diminished VY Canis Majoris applied here with equal force. Closer distance, same angular size, smaller physical dimensions. Current estimates settle UY Scuti at roughly 1,700 solar radii. A magnificent red supergiant by every measure, but one that no longer threatens the record held by Stephenson, 218. The margin between them exceeds what measurement uncertainty alone can explain. NML Cygni remains the most persistent rival, sitting approximately 5,300 light-years away in the constellation Cygnus. This red supergiant displays properties that some measurements place tantalizingly close to Stephenson 218. Certain analyses suggest radii approaching 2,000 solar radii, which would narrow the gap to a margin that falls within the combined error bars of both measurements. The debate over whether NML Cygni genuinely competes for the record continues in technical journals, with different research groups reaching different conclusions depending on which distance estimates and atmospheric models they employ. For now, the preponderance of converging measurements favors Stephenson 218, but NML Cygni stands close enough that future data could conceivably rearrange the ranking. Beyond our galaxy, an extraordinary object provides evidence that the physics governing red supergiants operates identically regardless of which galaxy hosts the star. WOHG 64 sits in the Large Magellanic Cloud, a satellite galaxy orbiting the Milky Way at a distance of approximately 170,000 light-years. Size estimates range from 1,500 to 2,000 solar radii, placing it among the largest stars known in any galaxy. Recent observations using the Atacama Large Millimeter Array by Onaka and colleagues revealed that WOHG 64 possesses an elongated, egg-shaped geometry rather than the spherical symmetry expected of an isolated star. The distortion suggests gravitational interaction with a companion object, stretching the star into an asymmetric configuration. WOHG 64 holds a unique distinction. It is the only red supergiant outside our galaxy whose shape has been directly resolved by imaging. Its existence confirms that the same stellar physics producing monstrous red supergiants in the Milky Way operates with identical results in neighboring galaxies. The universe runs the same software everywhere. Betelgeuse requires mention, not because it threatens the record, but because it occupies a singular position in human awareness of red supergiants. Sitting only about 700 light-years from Earth in the constellation Orion, Betelgeuse is by far the closest major red supergiant. You can see it on any clear winter evening, glowing with a distinctive orange-red hue at Orion's upper left shoulder. Its proximity makes it the most studied red supergiant in existence, and its dimensions, estimated between 750 and 1,000 solar radii, fall well below the record contenders. But Betelgeuse delivered a moment that illuminated both the public's fascination with stellar death and the difficulty of predicting it. In late 2019 and early 2020, Betelgeuse dimmed dramatically. Its brightness dropped to roughly 1/3 of its normal value, a change visible to the naked eye from suburban backyards. Headlines erupted worldwide. Was Betelgeuse about to explode? Were we about to witness a supernova in real time, visible in daylight, brighter than the full moon? The speculation was intoxicating, and, for a few weeks, it dominated science news cycles. The answer arrived with considerably less drama than the question deserved. Analysis published by Montargis and collaborators in 2021, using imaging from the Very Large Telescope's S-Sphere instrument, demonstrated that the dimming resulted from a large cloud of dust ejected from the star's surface, passing through the line of sight between Betelgeuse and Earth. This dust event coincided with a natural minimum in the star's regular pulsation cycle, producing a double dip in brightness that mimicked the behavior some models predicted for a pre-supernova star. Betelgeuse was not dying. It had sneezed. The star recovered its normal brightness within months and will likely continue burning for another 100,000 years before the core collapse that ends its existence. The episode demonstrated how difficult it remains to distinguish transient surface events from genuine signals of impending catastrophic death, even for the best-studied red supergiant in the sky. What separates Stephenson 218 from all these competitors is consistency. Multiple independent research groups using different observational techniques, different distance calibrations, and different atmospheric models converge on a diameter exceeding 2,000 solar radii. V. Y Canis Majoris has been revised downward. U. Y Scuti has been revised downward. N. M. L. Cygni remains uncertain. Stephenson 218 holds. But the data delivers a twist here that cuts across every intuition about what makes a star extreme. The largest star is not the most massive star. These two superlatives describe entirely different objects occupying different regions of the stellar population. Arctur 136a1, blazing within a dense star cluster in the Large Magellanic Cloud, carries a mass estimated between 170 and 250 solar masses. Based on the most recent analyses by Brands and collaborators published in 2022, revised downward from the initial estimate of roughly 300 solar masses reported by Crowther and colleagues in 2010. This star outweighs Stephenson 218 by a factor of 5 or more. Yet R136AL1 measures only a few tens of solar radii across. It is one of the most massive stars ever discovered, and it would fit comfortably inside the orbit of Mercury. The contrast is like comparing a lead bullet weighing 10 grams to a helium balloon filling an entire room, but weighing only 3 grams. The bullet is heavier. The balloon occupies the space. Mass and size measure fundamentally different properties of matter. The reason these two extremes diverge so dramatically lies in how the most massive stars evolve. Stars exceeding roughly 40 solar masses lose their hydrogen envelopes through stellar winds of extraordinary intensity, long before they can expand into red supergiants. The fierce radiation pouring from these objects accelerates surface material outward so aggressively that the hydrogen-rich outer layers are stripped away entirely, exposing the hot, compact interior. What remains is a Wolf-Rayet star, a class of objects first identified by French astronomers, Charles Wolf and Georges Rayet, in the 1860s. Wolf-Rayet stars are ferociously luminous and blistering hot, with surface temperatures exceeding 30,000 Kelvin. But they are small, typically only a few dozen solar radii across. They never become red supergiants because the raw material required for expansion, the hydrogen envelope, has been blown away before expansion can occur. The sweet spot for maximum physical size lies in an initial mass range of roughly 20 to 40 solar masses. Stars in this range are massive enough to evolve into red supergiants with enormous convective envelopes, but not so massive that stellar winds strip the hydrogen before expansion proceeds. Stephenson 218, born with an estimated 25 to 40 solar masses, sits squarely within this optimal band. Theoretical stellar structure models suggest a maximum red supergiant radius of approximately 2,500 to 3,000 solar radii for stars with ideal initial masses and mass loss histories. Stephenson 218, at roughly 2,150 solar radii, approaches the ceiling without breaching it. The agreement between observation and theory suggests that our understanding of stellar structure captures the essential physics, even at these extremes. Above the ceiling of individual stellar size sits another limit, the maximum mass with which any star can be born. As a forming protostar accretes material from its surrounding molecular cloud, its growing luminosity generates radiation pressure that pushes back against the infalling gas. Eventually, in the most massive cases, the radiation pressure matches and then exceeds the gravitational attraction pulling material inward. The forming star blows away its own food supply, terminating further growth. This feedback caps initial stellar masses at roughly 150 to 300 solar masses, depending on the metallicity of the parent cloud. Stars born from gas poor in elements heavier than helium couple radiation to matter less efficiently, potentially allowing higher masses to accumulate before the radiation barrier halts further growth. In the early universe, when metallicity was nearly zero, the first generation of stars may have exceeded current mass limits substantially, but those primordial giants burned out billions of years ago and can no longer be observed. The question of whether Stephenson 218 genuinely represents the largest star the universe currently contains depends on how thoroughly we have sampled the relevant population. The extremely large telescope, under construction at Cerro Armazones in Chile, with a primary mirror 39.3 meters across, will achieve resolving power and sensitivity roughly 4 times greater than the largest telescopes operating today. The Giant Magellan Telescope, rising at Las Campanas, Chile, will combine 7 mirrors into an effective aperture of 25.4 meters. The 30-meter telescope, planned for Hawaii, will extend similar capabilities across the Northern Hemisphere. From space, the James Webb Space Telescope already probes stellar populations in dusty galactic regions with infrared sensitivity, unmatched by any prior mission. The Nancy Grace Roman Space Telescope will survey enormous areas of sky at infrared wavelengths when it reaches orbit, ideally suited for discovering rare objects that might hide anywhere within the galaxy. With approximately 5 million red supergiants estimated to exist in the Milky Way at any given time, and fewer than a few thousand measured with precision sufficient to rank them, the current observational sample covers less than 0.1% of the total population. Statistical arguments alone suggest that larger stars may yet await discovery behind thicker dust clouds, in clusters not yet surveyed, in regions of the galaxy that current instruments cannot reach. Alternatively, Stephenson 218 may represent a genuine statistical outlier, a rare convergence of exactly the right initial mass, exactly the right mass loss history, and exactly the right evolutionary timing to produce dimensions at the extreme boundary of what physics permits. In that case, expanded surveys would find nothing larger because nothing larger exists to be found. The record could fall next year or stand for centuries. Only observation will settle the question. On the 6th of May, 1954, a 25-year-old medical student named Roger Bannister ran 1 mile on the Iffley Road track in Oxford in 3 minutes and 59.4 seconds. Before that afternoon, respected physiologists had argued that the 4-minute barrier represented a hard biological ceiling, a limit that the human body could not physically exceed. Bannister proved the barrier was not a wall, but a line on a map. Real enough until someone demonstrated that the territory beyond it was perfectly accessible. Within 2 years, multiple runners had broken 4 minutes. Records mark boundaries of possibility. They tell us what nature permits under the physical laws governing the system, but they also tell us what remains unexplored. And the history of every record ever set suggests that boundaries exist to be found, tested, and sometimes surpassed. Every record is also temporary in a deeper sense. Stephenson 218 does not occupy a stable position in the stellar hierarchy. It holds its title not as a permanent achievement, but as a transient phase, a brief moment within a stellar lifetime during which physical dimensions reach their maximum possible extent. This phase lasts less than 1% of the star's total existence. The red supergiant era is not a destination. It is a way station on a one-way road that terminates in the most violent event the physics of our universe permits. And that final event is already underway deep inside the core, hidden from the surface, hidden from our telescopes, ticking forward with the mechanical certainty of a countdown that no force in nature can interrupt. Iron built the Brooklyn Bridge in 1883, its cables and beams spanning the East River to connect Manhattan and Brooklyn across a gap that ferries had served for 2 centuries. Iron forged the railroad tracks that stitched a continent together after the Civil War. Iron plated the hulls of warships that decided the fate of nations. Iron framed the skyscrapers that defined the American skyline from the Woolworth Building to the Empire State. The language itself testifies to the metal's association with strength. Iron will, iron curtain, iron horse. Across every century of industrial civilization, iron has meant durability, resilience, the capacity to bear weight that lesser materials cannot support. Inside a dying star, iron means the opposite. Iron is the end. The nuclear binding energy curve describes how tightly the protons and neutrons within an atomic nucleus hold together. Light elements sit low on this curve. Their nucleons are loosely bound, and fusing them into heavier elements releases the difference in binding energy as usable power. This is the engine that drives every star in the universe. Hydrogen fuses into helium and releases energy. Helium fuses into carbon and releases energy. Carbon fuses into oxygen, neon, magnesium, silicon. And at every step, the products sit higher on the binding energy curve than the reactants. The difference powers the outward pressure that holds the star against its own gravity. Iron 56 sits at the peak. No element in the periodic table possesses a higher binding energy per nucleon. Fusing iron into anything heavier does not release energy. It consumes energy. The reaction runs in the wrong direction, absorbing power from the surroundings rather than contributing to the stellar energy budget. Iron is nuclear ash, the final waste product of stellar fusion, as useless for generating power as the cold charcoal remaining after a campfire burns out. You cannot reignite charcoal by adding more charcoal. You cannot sustain a star by accumulating more iron. Every gram of iron that forms in the core of Stephenson 218 is a gram that will never again contribute to holding the star upright. The core grows heavier while contributing nothing. Imagine a skyscraper whose structural steel columns are being replaced, one by one, with columns of styrofoam. From the outside, the building looks unchanged. The walls stand, the windows gleam, but inside, the load-bearing capacity diminishes with each substitution. At some threshold, the structure can no longer support its own weight. The collapse, when it comes, is not gradual. It is instantaneous and total. Silicon burning delivers the final load of iron. This phase, the last act of nuclear fusion in a massive star's life, lasts roughly 1 to 2 days, not million years, not 1,000 years, days. In those final hours, silicon-rich material surrounding the core fuses into iron group elements at a rate of approximately 1/10 of a solar mass per day. The iron core swells like a tumor, growing heavier with each passing hour while producing nothing that can prevent what comes next. When the iron core exceeds approximately 1.4 solar masses, it crosses a threshold calculated by the Indian-American astrophysicist Subramanian Chandrasekhar, who would receive the Nobel Prize in Physics in 1983 for this and related work on stellar structure. Below this mass, a quantum mechanical effect called electron degeneracy pressure supports the core against further compression. The Pauli exclusion principle forbids 2 electrons from occupying the same quantum state, creating a resistance to compression that operates independent of temperature. This resistance holds the core in a state of dense equilibrium, like a crowd of people packed so tightly in an elevator that no one can be pushed closer together regardless of how hard you shove. Above 1.4 solar masses, gravity overwhelms even this quantum mechanical barrier. Electrons are forced into protons through a process called inverse beta decay, each collision producing a neutron and a neutrino. The electrons that provided the degeneracy pressure vanish, consumed by the very protons they were preventing from collapsing. The last source of support disappears. The core falls. What happens next compresses events that would normally require astronomical timescales into fractions of a single second. The core implodes at approximately 1/4 the speed of light, roughly 75,000 kilometers per second. Material that occupied a volume comparable to the entire Earth collapses into a sphere roughly 20 kilometers across in less than 1 second. To visualize this compression, imagine taking the entire planet Earth, every ocean, every mountain range, every city and desert and ice sheet, and squeezing it all into a volume the size of Manhattan. Every gram of mass remains. The volume decreases by a factor approaching 1 billion. The density of the compressed core reaches approximately 200 trillion grams per cubic centimeter. The density of atomic nuclei themselves, a regime where individual neutrons and protons press against one another directly. A single teaspoon of this material would weigh several 100 million tons, more than the combined mass of every building in a major city. During this collapse, the neutrons created by inverse beta decay release a flood of neutrinos so vast that the numbers lose all human meaning. Roughly 10 to the 58th power individual neutrinos escape the collapsing core within a span of approximately 10 seconds. These ghostly particles interact so weakly with ordinary matter that most of them pass through the entire overlying stellar envelope without touching a single atom. Yet collectively, they carry away more energy than the star has radiated as visible light throughout its entire 20 million year lifetime. For a brief moment, the neutrino luminosity of the collapsing core exceeds the combined light output of every star in the observable universe. We know this is not theoretical speculation because we have detected it. On the 23rd of February, 1987, a blue supergiant in the Large Magellanic Cloud exploded as supernova. 1987, this approximately 168,000 light-years from Earth. Neutrino detectors around the world registered a total of 25 particles from that explosion. 12 were captured by the Kamiokande 2 detector in Japan. 8 arrived at the Irvine, Michigan Brookhaven detector in a salt mine beneath Lake Erie in Ohio. 5 reached the Baksan Neutrino Observatory in the Caucasus Mountains of the Soviet Union. 25 particles from an explosion in another galaxy. That handful of detections confirmed theoretical predictions about core collapse physics and contributed to the Nobel Prize in Physics awarded to Masatoshi Koshiba in 2002. A galactic supernova from Stephenson 218, roughly 8 times closer than supernova 1987A, would register thousands to tens of thousands of neutrino events across modern detector networks, including Super Kamiokande in Japan and IceCube at the South Pole. The data would arrive several hours before any electromagnetic radiation, because neutrinos escape the core immediately, while photons must wait for the shock wave to breach the stellar surface. The Supernova Early Warning System, an international network linking neutrino observatories worldwide, exists precisely to exploit this time gap, alerting astronomers to point their telescopes toward the right patch of sky before the first light arrives. But the shock wave that produces that light nearly fails. When the collapsing core reaches nuclear density, the strong nuclear force, which is repulsive at extremely short distances, halts the implosion abruptly. The infouling material bounces off the newly rigid neutron core like a rubber ball dropped onto concrete. This bounce generates an outward-moving shock wave carrying enormous kinetic energy. The shock should, in principle, blast through the overlying layers and tear the star apart. It does not. The iron nuclei above the bounce point require energy to disassemble into individual protons and neutrons. Each iron nucleus the shock encounters acts as an energy sink, absorbing momentum from the advancing wave. Within roughly 100 milliseconds, the shock stalls at a radius of perhaps 100 to 200 kilometers. Its energy exhausted, the stellar surface still nearly 2 billion miles away. For decades, this stalling problem tormented astrophysicists. Computer simulations consistently produced dead shocks and complete collapse into black holes without any visible explosion. Yet supernovae demonstrably occur. Something revives the shock. The leading explanation invokes those same neutrinos streaming outward from the neutron star. Although neutrinos interact feebly with matter, the densities in the region immediately behind the stalled shock are extreme enough that approximately 1% of the passing neutrino flux gets absorbed. That 1% deposits sufficient energy to reheat the stalled material and restart the outward expansion. Three-dimensional simulations conducted by groups led by researchers including Janka and Burrows from the 2010s onward have demonstrated that turbulent convection and hydrodynamic instabilities, particularly the standing accretion shock instability, play essential roles in channeling neutrino energy into shock revival. The explosion mechanism is not a simple spherical blast. It is a chaotic, asymmetric, turbulence-driven process that computational physics is still working to fully characterize. Once revived, the shock wave resumes its outward march through the stellar envelope. For a compact progenitor, this transit takes hours. For Stephenson 218, with its atmosphere extending nearly 2 billion miles from center to photosphere, the shock must traverse an ocean of tenuous material, even at thousands of kilometers per second. When it finally breaks through the surface, the supernova becomes visible to the outside universe. The star brightens by factors of billions within hours, radiating across every wavelength from radio to gamma rays. For a period of days to weeks, this single dying star will outshine every other star in the Milky Way combined. Peak luminosity reaches several billion times the sun's output. The galaxy contains roughly 400 billion stars. One red supergiant in its death throes temporarily surpasses them all. From Earth, 20,000 light-years away and behind heavy dust, the explosion might still be visible to the naked eye. The dust itself, heated by the blast, would glow intensely in infrared wavelengths, possibly appearing more prominent than the optical emission that the intervening material absorbs. The explosion would be classified as a Type II supernova, identified by hydrogen lines in its spectrum, a signature guaranteed by the thick hydrogen-rich envelope that defines every red supergiant. Behind the shock front, temperatures and densities reach conditions that enable nuclear reactions impossible during normal stellar evolution. Rapid neutron capture, a process physicists call the R process, builds elements heavier than iron by bombarding existing nuclei with neutrons faster than those nuclei can decay. Gold, platinum, uranium, thorium, and dozens of other heavy elements form in these extreme conditions, synthesized in seconds and scattered into space by the expanding debris. Every atom of gold in every ring and necklace on Earth was forged in a supernova explosion. Every atom of uranium generating power in every nuclear reactor was assembled in the seconds following a core collapse. Every atom of platinum in every catalytic converter cleaning exhaust on every highway was created in conditions no laboratory can replicate. When the Apollo 11 crew brought lunar rock samples back to Earth in July of 1969, chemical analysis revealed the same elemental composition found in terrestrial rocks. Because both the Earth and the Moon condensed from the same ancient cloud of supernova debris 4.6 billion years ago. We walk on processed stellar wreckage. We breathe it. We are built from it. At the center of the expanding debris, the nature of the remnant depends on how much mass remains in the collapsed core. If the remnant falls below roughly 2 to 3 solar masses, a neutron star persists, supported against further collapse by neutron degeneracy pressure and the repulsive component of the strong nuclear force. This object packs more mass than our Sun into a sphere roughly 20 kilometers across. Conservation of angular momentum during the collapse amplifies the original slow rotation of the massive star by factors proportional to the square of the radius reduction. A core that once rotated, perhaps once every few months, compressed by a factor of 100,000 in radius, spins tens to hundreds of times per second. Intense magnetic fields, amplified by the same compression, reach strengths a trillion times greater than Earth's magnetic field. The result can be a pulsar, a rapidly spinning neutron star emitting beams of radio waves that sweep across the sky like a lighthouse. The pulsar embedded in the Crab Nebula, remnant of the supernova recorded by Chinese astronomers in 1054 AD, still rotates 30 times per second after nearly 1,000 years. If the remnant exceeds roughly 2 to 3 solar masses, no known force can prevent continued collapse. The core compresses past the neutron star stage and forms a black hole, an object whose gravitational field is so intense that not even light can escape. For Stephenson 218, with an initial mass of 25 to 40 solar masses, reduced by extensive mass loss to perhaps 15 to 25 solar masses, the outcome remains genuinely uncertain. The dividing line depends on the equation of state of nuclear matter at extreme densities, a relationship that physics has not yet fully determined. A black hole from this star might reach 5 to 15 solar masses, comparable to the black holes detected through gravitational wave observations by LIGO and Virgo, whose first detection in September of 2015 and announcement in February of 2016 earned the Nobel Prize in Physics in 2017 for Rainer Weiss, Kip Thorne, and Barry Barish. And here, the most disorienting truth of all reasserts itself. We do not know whether Stephenson 218 still exists. The light reaching our telescopes tonight left the star approximately 20,000 years ago, when the last ice age still gripped the northern hemisphere and human ancestors were crossing the Bering Land Bridge into the Americas. The core may have collapsed 1,000 years ago, 5,000 years ago, 10,000 years ago. The photons carrying news of that cataclysm may be crossing interstellar space at this moment, racing toward Earth at the speed of light, bearing information about an event that occurred before the invention of writing, before agriculture, before the first permanent human settlement. Or the collapse may lie 100,000 years in the future, with the star continuing its slow nuclear countdown through stages we cannot observe at this distance. The finite speed of light seals the present behind an impenetrable barrier of elapsed time. We see the past. We always see the past. And for Stephenson 218, the past we see is 20 millennia deep. What we know with certainty is the cycle that follows. Material ejected at more than 10,000 kilometers per second, over 1,000 times faster than the space shuttle orbited Earth, will expand outward for millennia. It will form a supernova remnant glowing in radio, X-ray, and visible wavelengths, much like the Crab Nebula that still spans roughly 11 light-years across and continues expanding at 1,500 kilometers per second, nearly 1,000 years after the explosion that created it. Over millions of years, the enriched debris will mix with the surrounding interstellar medium, seeding molecular clouds with oxygen, carbon, silicon, iron, gold, and uranium. Those clouds will collapse under gravity to form new stars and new planets. The carbon in the bones of creatures not yet born, the oxygen in atmospheres not yet formed, the iron in the cores of worlds not yet assembled. Some of it will trace back to the interior of Stephenson 218. You are made of stellar debris, the carbon in your muscles, the oxygen in your lungs, the iron in your blood, the calcium in your bones, the phosphorus woven into your DNA. Every one of these atoms passed through the interior of at least one star that exploded before our solar system formed 4.6 billion years ago. You are not observing the universe from outside. You are the universe observing itself, assembled from the wreckage of ancient detonations, temporarily organized into a form capable of wondering where the raw materials came from. The death of Stephenson 218 will be among the most spectacular events to occur in the Milky Way over the next million years. But it will also be among the most generous. A single explosion, seeding surrounding space with the elemental ingredients for future solar systems, future oceans, future atmospheres, and perhaps future life. The star that dies does not know what will grow from its remains. The generations that follow do not remember the sacrifice that made them possible. Like the veterans who came home from the Second World War and built new lives on the foundation of the GI Bill in 1944, creating educational and economic opportunities for a generation that could never fully appreciate the cost. The dying star gives everything and receives nothing in return. The giving is the point. The cycle continues because the giving never stops. We journeyed through 20,000 light-years of interstellar dust to find a star that no optical telescope on Earth has ever seen. We learned how infrared light slips through cosmic fog that swallows 99.9999% of visible radiation, revealing entire stellar populations hidden since the formation of the galaxy. We measured the dimensions of an object so distant that its angular size collapses below the resolving power of every individual telescope ever built, and the numbers that emerged from interferometry and parallax and atmospheric modeling converged on a figure that breaks every intuition the human mind possesses. 2,150 solar radii, a volume 10 billion times greater than our Sun, a diameter that swallows Mercury, Venus, Earth, Mars, Jupiter, and Saturn, leaving Uranus bathed in the dim red glow of a stellar surface stretching across half the sky. We trace the life of this star backward through 20 million years, from the bloated red giant we observe today to the compact blue furnace it once was, a hot, dense sphere, 10 to 20 times the Sun's radius, burning hydrogen through the carbon-nitrogen-oxygen cycle at rates that exhausted a fuel supply 30 times larger than the Sun's in barely 1,000th the time. We watched the equilibrium break when the hydrogen ran out, the core contract, the envelope expand, the surface cool from searing blue to deep crimson as the star inflated across hundreds of millions of miles. We followed the countdown through helium, carbon, neon, oxygen, and silicon, each stage shorter than the last by orders of magnitude, until the final phase consumed its fuel in less than 2 days. We explored a surface where molecules form in the atmosphere of a star, where the photosphere thins to densities lower than any vacuum chamber on Earth, where the boundary between star and space dissolves into a gradient that no definition can fix. We watched the star breathe, expanding and contracting over cycles lasting years, its size never constant, its edges never sharp. We counted 3 mechanisms stripping mass from the envelope simultaneously, bleeding the star of material equivalent to our entire Sun every few thousand years. We compared Stephenson 218 against every rival that has claimed or contested the record. V.Y. Canis Majoris, revised downward. U.Y. Scuti, revised downward. N.M.L. Cygni, still uncertain. Betelgeuse, sneezing rather than dying. We discovered that the most massive star known, R136A1, weighs 5 times more than Stephenson 218, yet measures barely a fraction of its size. Because mass and volume obey different rules in different regions of the stellar population, we stared into the inevitable future, iron accumulating in the core, like a death sentence written one atom at a time. The Chandrasekhar limit breached, the core collapsing at 1/4 the speed of light. 10 to the 58th power neutrinos escaping in 10 seconds, carrying more energy than the star radiated in 20 million years of burning. A shockwave stalling, reviving, and finally tearing through nearly 2 billion miles of stellar material to produce an explosion brighter than 400 billion stars combined. And at the center, a neutron star, or a black hole, the largest known star in the universe, compressed into an object 20 kilometers across or crushed into a gravitational abyss from which nothing returns. At the opening of this journey, a paradox was posed, an object with 10 billion times the volume of our Sun, vast enough to swallow the orbit of Saturn, yet less dense on average than the best vacuum any laboratory has ever achieved. That paradox now has its answer. The core of Stephenson 218 is denser than atomic nuclei, crushed to conditions where quantum mechanics governs the behavior of matter. The envelope is emptier than interplanetary space, a thin haze stretching across billions of miles, held aloft by energy flowing outward from burning shells deep below. Immensity and emptiness coexist within a single object, not as contradiction, but as consequence. The same equations, the same physics, the same fundamental laws that govern our modest Sun produce this result when applied to different starting conditions. the grandeur and the void are two faces of one reality. We are brief creatures on a small planet orbiting an ordinary star in an unremarkable arm of a spiral galaxy among 2 trillion galaxies scattered across the observable universe. The sun dominates every aspect of human existence, providing the energy that drives weather, agriculture, and the biological processes sustaining every living organism on this world. And it would vanish as an invisible speck inside the volume of Stephenson 218. Perhaps that comparison should diminish us. Perhaps knowing that our star is less than a rounding error beside the largest known stellar object should reduce human concerns to insignificance. But we are the ones who found it. We are the ones who measured it from 20,000 light-years away using photons that departed before writing, before agriculture, before the first permanent settlement on Earth. We are atoms that were once inside ancient stars, now assembled into forms that can calculate the dimensions of the largest stars currently burning. We are the universe examining its own extremes. Perhaps that is the deepest paradox of all. The smallest observers measuring the largest object, the briefest lives comprehending processes spanning 20 million years, the most fragile structures understanding the most violent deaths the cosmos permits. We have mapped the boundaries of what nature allows. And we have done it from a pale blue dot that the largest known star could swallow without noticing. The light arriving at our telescopes tonight left Stephenson 218 when glaciers still covered the northern continents and human beings had not yet learned to plant seeds. Those photons have crossed 20,000 years of space and time to reach instruments built by descendants of the same stardust that fuels the object they are observing. We do not know whether the star still burns or has already died. We know only what ancient light tells us, and ancient light says this. Somewhere in the Milky Way, invisible to human eyes, a star once burned with the volume of 10 billion suns and the density of almost nothing at all.